In the last video, we talked about the relationship between the physical properties of a substance and the strengths and types of intermolecular forces present. These properties include things like melting point and boiling point, enthalpy of vaporization and enthalpy of fusion, vapor pressure, viscosity, and surface tension. Today we're going to focus on the different types of solids, and we'll use particulate level representations to help us with this. Let's start with ionic solids. Just to review, ionic solids are crystalline solids that are composed of metal cations and non-metal anions that are held together by electrostatic attraction. These attractions are also known as ionic bonds. The attractions obey Coulomb's law. The larger the charges on the ions, the greater the attractions. The smaller the ionic radii are, the greater the attraction. The ions line up in a regular repetitive pattern in such a way as to minimize the repulsive forces and maximize the attractive ones. This arrangement is called a crystal lattice. Because the attractions between the ions are very strong, ionic compounds are characterized by high melting points. It takes a lot of energy to overcome the electrostatic attractions. They also have low volatility, which means it takes a lot of energy to get them into the gas phase. For example, the boiling point of sodium chloride is 1,465 degrees Celsius. Ionic solids have low vapor pressures. Those little ions are not inclined to break free from the surface of a sample. Ionic compounds are very strong, and it takes a large amount of mechanical force to break them. However, they also tend to be brittle, and if you hit them just right, they will shatter rather than bend. This picture illustrates the force of a hammer breaking off part of a crystal. When the hammer hits the crystal, the ions are shifted slightly so that similarly charged ions are next to each other and repel each other. That's why ionic crystals tend to break along smooth cleavage planes. Most ionic solids are soluble in polar solvents such as water. When they're dissolved, they will often exhibit ion-dipole intermolecular forces. Most ionic solids do not dissolve in nonpolar substances because the attractions between the ions are greater than the attractions between the ions and the nonpolar substance. Ionic solids do not conduct electricity when they're in their solid form. However, they can conduct electricity when they are melted or dissolved because their ions are free to move. The higher the ion concentration is in a solution, the better the electrical conductivity will be. Now let's talk about metallic solids. Metallic solids are crystalline solids formed by metal atoms. These atoms are held together by metallic bonds, which can be described as a uniform distribution of atomic nuclei in a sea of delocalized electrons. Although the core electrons stay localized around the atom, the valence electrons are free to move throughout the solid. The bonding results from the attractions between the nuclei and these delocalized electrons. Metallic solids typically have high melting points and high boiling points, but there are some exceptions, including mercury, which is liquid at room temperature. Metals have low volatility, which means they don't vaporize easily. Because the electrons are delocalized, it's possible to move the cations around without having to put in a lot of energy, like you would have to do if you were breaking an ionic or covalent bond. Because of this, metals tend to be soft. They also tend to be malleable, which means you can pound them into shapes, and ductile, which means you can stretch them into wires. Metals have a characteristic metallic luster. Electrons on the surface can bounce back light at the same frequency that the light hits the surface, so metals appear shiny. Because the electrons are delocalized, metals are great conductors of electricity. They're also very good conductors of heat. Now let's talk about molecular solids. Molecular solids are comprised of covalent compounds between nonmetals or neutral atoms. They're essentially groups of individual molecules held together by intermolecular forces, such as London dispersion forces, dipole-dipole forces, or hydrogen bonding. These forces between the molecules are relatively weak, so molecular solids tend to be soft and flexible. They tend to melt at pretty low temperatures, and they evaporate easily. Molecular solids are not good conductors of electricity because electrons are localized within the individual molecules and they can't move around easily. Polar molecular solids, like sugar, are soluble in polar solvents like water. But it's important to note that unlike with ionic solids, which break into their ions when they're dissolved in water, the molecules in molecular solids don't break apart. They just separate. In other words, no bonds are broken. Intermolecular forces, however, are overcome. Molecular solids consisting of large molecules are generally less volatile than those consisting of small ones. This means they're less likely to evaporate. And this is because London dispersion forces are stronger for larger molecules. The shape of the molecules in the molecular solid also plays an important role in its physical properties. Molecules that are bulky or bent do not stack up well. This weakens the dispersion forces between the molecules, and compounds with these bent structures are often liquid at room temperature. Molecular solids can be ductile or brittle or a combination. It all depends on what types of compounds are making up the solid. Examples of molecular solids include sucrose, or table sugar, solid water, also known as ice, solid carbon dioxide, known as dry ice, solid iodine, and others. Lastly, let's talk about covalent network solids. Covalent network solids are made of chains of nonmetal atoms or molecules that are held together by covalent bonds. A perfect single crystal of a covalent solid is effectively a single giant molecule. Elements in the carbon group, like carbon and silicon, often form covalent network solids. Covalent network solids have very high melting points. In order to melt the solid, you have to actually break the covalent bonds that are holding the solid together. This is very different than what you see in molecular solids, where you're just trying to overcome the intermolecular forces. Covalent network solids are characterized by hardness and strength. Covalent network solids often have very different structures, even when they're made from the same elements. In graphite, for example, carbon atoms form two-dimensional network solid sheets. The sheets stack on top of each other and are attracted to each other through intermolecular forces. The sheets can slide over each other, and this makes graphite very useful in pencils. As you write, layers of graphite slide off your pencil and onto the paper. Diamond is also comprised of carbon atoms, but in diamond, each carbon atom is bound to 4 other carbons in a 3-dimensional giant covalent structure. Diamond has a very high melting point, almost 4,000 degrees Celsius. Diamond is very hard, and it does not conduct electricity because all the electrons are held very tightly and they're not free to move. It's also insoluble in water, and it doesn't dissolve in other solvents either. Examples of network covalent solids include diamond, graphite, silicon dioxide or sand, and silicon carbide. It's important not to confuse covalent network solids and molecular solids. Because of that network of covalent bonds, covalent network solids are some of the strongest substances. Molecular solids tend to be weaker than covalent network solids, ionic solids, even metallic solids, because they're basically just a bunch of molecules held together by intermolecular forces, rather than bonds. Now let's talk about large biomolecules and polymers. In large biomolecules or polymers, intermolecular forces can occur between different molecules or between different parts of the same large molecule. The properties and function of these molecules depends strongly on the shape of the molecule, and the shape is largely dictated by intermolecular forces. Let's take a look at an example. Enzymes. These huge complex structures take advantage of many different types of intermolecular forces to carry out their tasks. Intermolecular forces help give enzymes their shape, and they help them bind to the substrates that they are linking together or pulling apart or breaking down. Let's look at another example, DNA. The hydrogen bonds between the base pairs are essential to both DNA's shape and its function. Let's summarize. There are several different types of solids, and their properties are determined by the types of intermolecular forces that are at work. The four main types of solids we talked about today are ionic solids, covalent network solids, molecular solids, and metallic solids. And we also talked about biomolecules, which depend on intermolecular forces for both their shape and function.